Unit 1, Scalar fields and their gradients. How would you determine the path of steepest ascent on a hill? Comment this. Structure, introduction, expected learning outcomes, scalar fields, defining a scalar field, representations of a scalar field, gradient of a scalar field, and the directional derivative. The gradient of a scalar field, the directional derivative of a scalar field. Summary, terminal questions, solution and answer. Study guide. In this unit, you will study about scalar fields and their gradients. Before studying this unit, you should revise Unit 1 and 2 of the Physics elective BPHCT-133 entitled Mechanics. You should also be familiar with the basic concept of differential calculus, which you have studied in school. These concepts are also explained in the Mathematics elective BMTC 131. For calculating the gradient, you must know how to obtain the partial derivatives of function. You can revise this from the appendix of this unit. Partial derivatives are also explained in the Mathematics course BMTC 132, which you may revise. A brief summary of the basic concept of vector algebra and derivatives of vector functions is provided in Appendix A1 of this block. You may like to go through it before studying this unit. And believe me, if I were again beginning my studies, I should follow the advice of Plato and start with mathematics. Galileo Galilei. Introduction. In the first two units of Block 1 of the first course in physics entitled Mechanics BPHCT 131, you have studied the basic concept of vector algebra. You have learned how to add, subtract, and multiply vector quantities using both the geometric and algebraic representations of vector. You have seen examples of vector, their sum and difference, as well as scalars and vector products in physics in Unit 2. You have also studied the preliminary concept of vector differential calculus. You now know about vector functions or vector valued functions and how to obtain their derivatives with respect to a scalar variables. You have also learned how to obtain the derivatives of vector and scalar products of vectors. In this unit, we further study vector differential calculus. In section, we introduce the concept of scalar fields. In section, you will learn about the gradient and directional derivative of a scalar field. You may wish to know why do you need to learn this concept. To understand this, consider the example of a bar, plate or cylinder that is heated non-uniformly, so its temperature at different points is different. The temperature distribution of the bar, plate, cylinder is represented mathematically by a scalar field. If we now wish to know the rate of change of the temperature within the object in any given direction, we need to determine the directional derivative of this temperature distribution. For this, we must know the gradient of the scalar field. In section, you will learn how to determine the gradient of a scalar field. Then you will learn how to determine the directional derivative of the field in section. Expected learning outcomes. After studying this unit, you should be able to explain the concept of scalar field and give example in physics. Determine the gradient of a scalar field and determine the directional derivative of a scalar field. Don't forget, in your written work, always use an arrow above the letter you used to denote a vector, example R. Use a cap above the letter you use to denote a unit vector, example R cap. Scalar fields. In Block 1 of the course BPHCT-131 entitled Mechanics, you have learned about vector functions which can depend on one or more variable. When we are describing physical quantities, one obvious variable with which many physical quantities change is time. However, you have also studied about many physical quantities which have different values at different points in space. A function that describes a physical quantity at different points in space is called a field. As physical quantities are either scalar or vector in nature, we can have both scalar and vector fields. In this section, we focus on scalar field. For example, the density of air in the Earth's atmosphere is a scalar quantity that changes with the altitude above the sea level. Similarly, the atmospheric pressure is also a scalar having different values at different altitudes. It is also different at different points around the Earth. The temperature of an unevenly heated plate is a function of both space coordinates and time. All these are examples of scalar fields. Let us discuss the concept of a scalar field in more detail. You have studied in Unit 2 of BPHCT-131 that every point in space can be denoted by the position vector. R vector equal to xi cap plus yj cap plus zk cap. So, we could also say that corresponding to every point represented by a position vector R vector, we have a unique scalar quantity fr vector. Defining a scalar field is a function that assigns a unique scalar to every point in given region. So you can say that it is essentially a scalar function of space coordinate. As you know from your school mathematics, every point in space may be specified by the Cartesian coordinates of the point x, y, z. So we can write the scalar function or scalar field as f equal to f of x, y, z. This means that for every point x, y, z in space, there exists a unique scalar quantity given by f of x, y, z. The gravitational potential energy of an object near the surface of the earth in a simple example of a scalar field. Suppose we take the xy plane to lie on the surface of the earth and z axis to point upward, then the gravitational potential energy of the object is given by phi of xyz equal to mgz, where m is the mass of the object. In this case, the scalar field depends only on the z coordinate and is therefore a one-dimensional scalar field. Temperature, pressure, and density are examples of some other physical quantities which are scalars and can be represented by scalar field. For example, the temperature on a perfectly flat hot plate can be described by T of xy equal to 250 by x square plus y square plus 1. Temperature on a flat hot plate heated at the center is a two-dimensional scalar field. At the center of the temperature is very high. The temperature is lower as we move away from the center of the hot plate. T of xy gives us the temperature at any point xy on the surface of the hot plate. Figure, since the surface of the plate is two-dimensional, the value of T depends only on x and y. This is an example of a two-dimensional scalar field. Another example of a scalar field is the electric potential in free space at a distance r from a point charge q. It is given by Vr equal to 1 by 4 pi epsilon 0 of q by r volt, where q is measured in coulomb and r in m. Here epsilon 0 is permittivity or free space. If we consider the origin of the Cartesian coordinate system to be located at the charge, we can also write the electric potential at a distance r as V of xyz equal to 1 by 4 pi epsilon 0 of q by x square plus y square plus z square whole to the power half. This function describes a scalar field in 3 dimensions. In this unit, we are interested in finding out about the rate at which these fields change in space. In order to understand physically the rate of change of scalar fields, it is a good idea to learn how to represent them pictorially. So our next question is, how do we represent the scalar fields in diagram? It is possible to represent scalar field visually using what are called contour curves or contour surfaces. Let us see how. Representations of a scalar fields. Have you heard about contour lines? Do you remember the map you studied in your school geography courses? How do we show the heights of places on a map? Recall from school geography courses that this is shown using contour lines or contour curves. On a map, contour lines or contour curves context connect this point which are at the same height means elevation lines above a fixed level. This is usually the sea level. Remember, the contour lines never cross each other. If you walk along a contour line, you neither gain nor lose elevation. Contour lines are useful because they tell us about the shape of the land surface. Imagine that you are standing at the same point on a hill at a certain height. Figure A. Study figure B. It shows the contour curve, one joining all points of the height on the hill. In fact, each contour curve joins all the points on the hill which are at the same height. Suppose we write the height at a point xy as z of xy. Then the contour curves is figure B join the points z xy constant. The contour curves are then a pictorial representations of the scalar function z of xy. A, B. A. Imagine you are standing somewhere on a hill. Contour map of the hill. A plot of several contour lines is called a contour map. 1, A2, B1, 3. We have already described the scalar field for the gravitational potential energy in equation A. You know that all points in any given contour curve in figure B depict points which lie at the same height above the ground. So as per equation A, it is also the curve on which the gravitational potential energy of the object would be constant. Thus, the set of contour curves shown in figure B can be used to depict the gravitational potential energy field given by equation A. In general, a contour curve is defined as a curve in 2 dimensions on which the value of scalar field f of xy is constant. F of xy equal to c. Contour map for the temperature of the hot plate. Each contour line corresponds to one value of the temperature defined in equation B. A plot of several contour curves is called a contour plot or a contour map. The contour map for the temperature of the hot plate is shown in figure. We now ask, what else can we determine from the contour map of a scalar field? Study figure once again. Look at the region around the point A and B. In it, note that the contour curves around A are close together and those around B are far apart. What does this tell us? Imagine that you are climbing the hill along a steep path, but 2 in figure B, since the height above the sea level changes rapidly along this path. The contour curve, the curves of equal height above the ground, lie close to each other. On the other hand, if you walk along path 3, where the contour curves are far apart, the height above sea level changes comparatively slow. So the spacing of the contour curves on a contour map indicates how rapidly the function is changing if the contour curves lie close to each other. The scalar field changes rapidly in that region. If these are far apart, the change in the scalar field is slower. So far we were talking about scalar function in two dimensions. You may now ask, how do we represent scalar fields in three dimensions? One way of doing this is to define contour surface as follow. Contour surfaces are the surfaces on which the value of its three-dimensional scalar field is constant. Contour surfaces of constant electric potential are surfaces of concentric spheres. The radii of the spheres is defined by equation P. Equipotential surfaces. So if a scalar field is defined by the function phi xyz, the contour surface would be the collection of all points xyz for which the value of phi is constant. Say C, the contour surface is defined by the equation phi of xyz equal to C. We get different color surfaces for different values of C. A collection of such contour surfaces would then be representation of the scalar field phi of xyz. For example, for the scalar field described by equation D, the contour surfaces are the surfaces of constant electric potential given by V of xyz equal to V0 and are described by the equation 1 by 4 pi epsilon 0 of q by x square plus y square plus z square to whole to the power half equal to v0 equal to x square plus y square plus z square equal to r square. Where r is a constant, you can see that the contour surface given by equation A is a sphere whose radius is given by the equation r equal to q by 4 pi epsilon 0 v0. For different values of V0, R is different. The contour surface for different values of V0 are surfaces of concentric spheres as shown in figure. Any contour curve on which a potential is constant is called an equipotential curve. The contour surfaces described by equation A are called equipotential surfaces. Similarly, contour curves or surfaces for the temperature field are called isothermals. Now that we have defined a scalar field and represented it pictorially, we would like to know what is the rate of change of a scalar field in a given direction. For example, if you are standing somewhere on a hill, you may wish to find out the direction of the fastest way down or the steepest slope. So that you may avoid it, you would of course like to take the direction of least slope to climb down, lest you fall. Recall from school calculus that the slope also gives us the rate of change. We use this fact to arrive at the concept of the gradient operator and the directional derivative. You will learn in the next section that the gradient of a scalar field gives the maximum rates of the change of the function. So let us define the gradient of a scalar field, then we shall use it to explain the concept of directional derivative. Gradient of a scalar fields and the directional derivative. In a school calculus course, you have learnt about the concept of the slope of a function. Suppose you hit a thin rod at one of its ends, then the temperature T of the rods would be different at different points along its length. Suppose you wish to know the rate at which T changes along the rod. Let us treat the rod as a one-dimensional object and choose the x-axis to be along the rod. So t equal to tx is a function of x. Then the question is, if you change x by a small amount dx, by what amount does tx change? Let this change in tx be denoted by dt. From school calculus, you know that the answer is dt equal to dt by dx of dx. So, if x is changed by an amount dx, t changes by an amount dt given by equation, the derivative dt by dx is proportionally factored. It gives the rate of change in tx along the x direction. In this example, the temperature is a function of just one variable x measured along the length of the rod. Now imagine is a closed room with a fire lit in the fireplace or a room heater. In one corner, the temperature in the room is described by the scalar field T of xyz. Standing at a point in the room, say at the center, we could ask at what rate the temperature changes as we move away from the point in the x direction, say by a distance delta x. From your school calculus course, you know that the rate of changes of a two or three dimensional function is described by partial derivatives of the function. Thus, the partial derivatives of t of xyz with respect to x gives its rate of change in the x direction. Can we then find out the direction in which the rate of change of temperature is maximum? The answer is yes, we can. In terms of the partial derivatives of the scalar field T of xyz at this stage, you may like to refresh your knowledge of partial derivatives. For this, you should study the appendix to the unit before studying further. Let us now answer the question, how do we express the maximum rate of change of any scalar field? To do so, we define the gradient of a scalar field using the concept of partial derivatives. The gradient of a scalar field. Let us begin by considering a two-dimensional scalar field f of xy. Then we shall generalize the result to f of xyz considered to point p of xy and q of x plus delta x and y plus delta y in the region in which the scalar field f of xy is defined. Suppose the position vector of the points are r vector and r plus delta r respectively. Then the change in f of xy as one goes a small distance from the point P to point Q is given by delta f equal to f of x plus delta x, y plus delta y minus f of xy. Do the steps from equation A to equation C yourself on a separate piece of paper. As you study them, you will understand this concept better. To get to the final result, we add and subtract a term f of x and y plus delta y and write delta f equal to f of x plus delta x, y plus delta y minus f of x, y plus delta y plus f of x, y plus delta y minus f of xy. B. Then we divide and multiply the two terms on the right hand side of equation B by delta x and delta y respectively and write delta f equal to f of x plus delta x, y plus delta y minus f of xy plus delta y by delta x into delta x. F of xy plus delta y minus f of xy by delta y into delta y. Next, we consider the terms on the right hand side of equation C and take the limits of delta f as delta x to 0 and delta y to 0. Limit delta x to 0, delta y to 0, delta f equal to limit delta x to 0, delta y to 0, f of x plus delta x, y plus delta y minus f of x and y plus delta y by delta x into delta x plus limit delta x tends to 0, delta y tends to 0, f of x y plus delta y minus f of xy by delta y of delta y. Using the definition of the partial derivative in equation 1 of the appendix to this unit, we can write limit delta x tends to 0, f of x plus delta x, y plus delta y minus f of x and y plus delta y by delta x into delta x equal to delta f x of y plus delta y by delta x and dx, and limit delta y tends to 0, f of x y plus delta y minus f of x y by delta y into delta y equal to delta f of x y by delta y into dy. Using this result, we can write equation D as limit x tends to 0, y, delta y tends to 0, delta f equal to limit delta y tends to 0, delta f of x y plus delta y by dx and dx plus limit delta x tends to 0, delta f of xy by delta y into dy equal to delta f of xy by delta x dx plus delta f of xy by delta y dy. The left hand side of the equation E defines a function df called the total differential of f. Thus, the total differential of a two-dimensional scalar field f of xy of f of, to keep the writing of the equation simple, is df equal to diff f by diff x dx plus diff f by diff y dy. We can generalize this result to f of x, y, z, for which the total differential df is df equal to diff f by diff x dx plus diff f by diff y dy plus diff f by diff z dz. The significance of df is that it is a good approximation to delta f if dx is equal to delta x, dy is equal to delta y, and dz is equal to delta z represent small changes in x, y, and z respectively. So df becomes a better and better approximation of delta f as dx, dy, and dz become smaller. We are now ready to introduce the concept of the gradient. We can rewrite equation B in a more convenient form as follows: df equal to diff f by dx I cap plus diff f by diff y j cap plus diff f by diff z k cap into dx I cap plus dy z cap plus dz k cap. You must verify by simplifying equation A that it is indeed the same as equation B. You can also identify that dx I cap plus dy j cap plus dz k cap is equal to dr vector. Is the change in the position vector the vector diff f by dx I cap plus diff f by diff y j cap plus diff f by d j k cap is equal to grad f equal to reverse delta f is defined as a gradient of the scalar field f. Using equations BC, you can write equation A as df equal to reverse delta f into dr. The symbol reverse delta is pronounced as del and del f as grad f. Equation C tells us that the gradient of a scalar field is a vector. Note that del f is a vector such that the change df in f for an arbitrarily small change dr is given by equation. Let us interpret the physical meaning of this result. Suppose the angle between del f and dr is given by theta, then we can write equation as df equal to del mod of del f mod of dr cos theta mod of del f dr cos theta. The gradient of a scalar field is perpendicular to the surface on which the scalar field is constant. Del f dr f of xyz equal to constant. What happens when theta is 90 degree? That is, del f is perpendicular to dr. Equation A tells us that if f is equal to 0, which means that f is constant. In other words, the value of the scalar field f is constant along the direction perpendicular to its gradient. We can express this result as follows. Don't forget, the vector del f is a perpendicular normal to the curve or surface f equal to constant. We now keep dr constant and find the change df in various directions by changing theta. Then we ask for what value of theta or in which direction is the change maximum. From equation, you can immediately say that df is maximum when theta is 0 degree. This means that for a fixed dr, the change df is maximum when you move in the same direction as del f. In addition, the rate of change of f with respect to r is given by df by dr equal to mod of del f cos theta. So the maximum rate of increase of the scalar field f space is along the direction of the gradient of the field del f, and its magnitude is df by dr of max is equal to mod of del f. The magnitude of del f gives the maximum rate of change of the scalar field in space. Don't forget. In the same way, when dr is in the direction opposite to del f, then theta is 180 degree in equation, and df by dr equal to minus mod of del f. This is then the direction in which the rate of decrease of the field f is maximum. We have arrived at the definition of the gradient of a scalar field and learned its physical meaning. Let us put this result together. Recap. Gradient of a scalar field. The gradient of a scalar field is defined as follows. Grad f equal to del f equal to diff f by diff x I cap plus diff f by diff y j cap plus diff f by diff z k cap. For a scalar field f of xy in two dimension, del f equal to diff f by diff x I cap plus diff f by diff y j cap. The magnitude of del f gives the maximum rate of the change of the scalar field in space. The direction of del f is perpendicular to the curves or surface f equal to constant. You should note that f of xyz is scalar field because it assigns a scalar quantity to every point xyz in space. On the other hand, the gradient delta del f of the scalar field f assigns a vector quantity to every point in space. Therefore, del f is a vector field. Let us further understand the concept of gradient with the help of example from physics and calculate its value. In physics, many vector quantities can be expressed as the gradient of a scalar field. For example, we can express the gravitational force as a vector equal to minus del V, where V is the gravitational potential energy. The electric field E due to a static charge distribution is the gradient of the electric potential E equal to minus del phi. Let us take up an example to calculate the gradient of a potential field. Example 1.1, gradient of a scalar field. The potential that represent an inverse square force is V of x, y, z equal to k by x square plus y square plus z square to the whole to the power half, where k is a constant. Using the definition f equal to minus del v, calculate the component of this force. Solution. We use the definition a vector minus del v and calculate the gradient of v x y z from equation A. Thus we have f x I cap plus f y j cap plus f z k cap equal to minus diff v by diff x I cap plus diff v by diff y j cap plus diff v by diff z k cap, or fx equal to minus diff v by diff x, fy equal to minus diff v by diff y, fz equal to diff v by diff z. Let x square plus y square plus z square equal to t, then diff by diff x of 1 by x square plus y square plus z square whole to the power half equal to d by dt 1 by t to the power half of dt by dx minus half of 1 by t to the power 3 by 2 into d by dx x square plus y square plus z square equal to minus 1 by 2t to the power 3 by 2 into 2x equal to minus x by x square plus y square plus z square whole to the power 3 by 2. So we have to calculate the above partial derivatives of v of x, y, z. Now fx is equal to minus d v by dx is equal to minus k d by dx of 1 by x square plus y square plus z square of half equal to minus k of minus x by x square plus y square plus z square whole to the power 3 by 2. Read the margin remarks. Equal to kx equal to kx by x square plus y square plus z square whole to the power 3 by 2. Similarly, fy is equal to minus dv by dy equal to ky by x square plus y square plus z square whole to the power 3 by 2, and fz equal to dv by dz is equal to kz by x square plus y square plus z square whole to the power 3 by 2. Do the steps of example 1.1 yourself on a separate piece of paper. There is f equal to minus del v equal to k by x square plus y square plus z square whole to the power 3 by 2 of x I cap plus y j cap plus z k cap equal to k r vector by r cube equal to k by r square of r cap, since r vector equal to r into r cap, where r vector equal to x I cap plus y j cap plus z k cap and r equal to x square plus y square plus z square whole to the power half. Example 1.1 illustrate an important application of the gradient in physics. We use scalar and vector field functions to represent various physical quantities. They are often related in this way. A vector field is a scalar multiple of the gradient of some scalar field function. This also suggests that we can construct a vector field from a scalar field by taking its gradient. Notice that in this section we have used the term vector field. You will learn more about it in unit 2. Let us take another example for calculating the gradient of a scalar field. Example 1.2, gradient of a scalar field. Determine the gradient of an arbitrary function fr where r equal to x square plus y square plus z square whole to the power half. Use this to determine the gradient of the function phi of xyz equal to k by x square plus y square plus z square. Solution: we use equation A with phi equal to fr del phi equal to df by dx I cap plus df by dy j cap plus df by dz k cap. Using the chain rule from calculus, we can write df by dr equal to df by dr into dr by dx. Df by dr of d by dx of x square plus y square plus z square whole to the power half, that is r equal to x square plus y square plus z square whole to the power half. Df by dr of half into 2x by x square plus y square plus z square whole to the power half equal to x by r df by dr, that is r equal to x square plus y square plus z square whole to the power half. D by dx of x square plus y square plus z square whole to the power half equal to 1 by 2 of x square plus y square plus z square whole to the power half minus 1 into 2x. Similarly, df by dy equal to df by dr into d by dy of x square plus y square plus z square whole to the power half equal to df by dr of 1 by 2 into 2y by x square plus y square plus z square whole to the power half equal to y by r into df by dr, and df by dz equal to df by dr into d by dz of x square plus y square plus z square whole to the power half equal to df by dr into half into 2z by x square plus y square plus z square whole to the power half z by r df by dr. Substituting 2, 3 and 4 in 1, we get del fr equal to s by r of df by dr I cap y by r df by dr j cap z by r df by dr k cap equal to 1 by r df by dr xi plus yz plus zk or v fr df by dr r by r df by dr into r cap, where r cap is a unit vector along r. In physics, we encounter many scalar functions of r, and hence equation 5 is an important result. To determine the gradient of the scalar field phi of xyz is equal to k by x square plus y square plus z square, we write it as phi equal to k by r square equal to fr. Using equation 5, we can write del phi equal to del f of r equal to del by d by dr of k by r square into r cap equal to minus 2k by r cube of r cap equal to minus 2k by r cube into r cap. SQ1, gradient of a scalar field. Comment this. The gradient of a scalar field is important in physics because we use it to express in relationship between a conservative force and a scalar potential. A conservative force field is related to a scalar potential V as F equal to minus del V. You have studied about conservative force in your first semester course BPHCT-133 entitled Mechanics. You know that force like the electrostatic force, The gravitational force and the spring force are conservative force. Each of these forces can be related to a corresponding potential function. The negative sign in this equation is important. It says that the force is in the direction of the negative gradient of the potential. This tells us, for example, that the gravitational force is directed from the point of higher gravitational potential to lower gravitational potential, like from top of a building to the ground. In SAQ2, you will solve problem on some application of the gradient of a scalar field. SAQ2 applications of the gradient comment this. So far we have defined the gradient of a scalar field, which tells us the direction of maximum space rate of the change of the scalar field. We can determine the rate of change of the scalar field in any direction by defining the directional derivative of the scalar field. F in terms of the gradient of the scalar field. This is what we do now. The directional derivative of a scalar field, directional derivative p x0 y0 z0 q x y z s cap. Let us find the rate of change of f of x, y, z with the distance s at a given point p of x0, y0, z0 in the field and in a given direction. Figure. This is called the directional derivative df by ds of the functional with distance s. Let s cap be the unit vector in the direction in which we want to find the rate of change of the scalar field. Let the unit vector s cap be defined by s cap equal to a I cap plus b j cap plus c k cap. Let us start from the point P and go a distance s greater than equal to 0 along the direction of the unit vector s cap. To reach the point Q of xyz, we can write the displacement vector pq vector equal to s of s cap as s vector equal to x minus x0 I cap plus y minus y0 I j cap plus z minus z0 k cap. We can also write s in terms of the unit vector s as s equal to sa I cap plus b j cap sc k cap. Comparing equation b and c, we get x minus x0 equal to sa, y minus y0 equal to sb, z minus z0 equal to sc, or x is equal to x0 plus sa, y equal to y0 plus sa, z equal to z0 plus sc. What do equations tell us? You can see that the variable x is equal to xs, y equal to ys, and z equal to zs are all functions of a single variable. S equations are called the parametric equations of the line PQ, which passes through the points x0, y0, z0, and xyz with the parameter as s. Remember that here s is the distance between the point P and Q measured along the line PQ. So if we substitute x, y, and z in terms of s, the function f of x, y, z becomes a function of a single variable, the parameter s. We can now write the directional derivative df by ds using the following chain rule from calculus from the derivative of a function f of x, y, z, where x, y, and z are function of s. Df by ds equal to df by dx dx by ds plus df by dy dy by ds plus df by dz dz by ds. In equation a to c, note that since f is function of x, y, and z, the derivative of f with respect to x is a partial derivative. Since x is a function of only s, the derivative of x with respect to s is an ordinary derivative. From equation D, we have dx by ds is equal to a, dy by ds is equal to b, dz by ds is equal to c. So equation A, which gives the expression for the directional derivative of f, now becomes df by ds is equal to df by dx of a plus df by dy b plus df by dz c. We now make use of expression of the gradient of a scalar field given by equation A, del f equal to del df by dx I cap plus df by dx j cap plus df by dz k cap. Then we take the scalar or dot products of the vector del f and s cap and get del f into s cap into df by dx I cap plus df by dy j cap plus df by dz k cap into a I cap plus b I j cap plus c k cap equal to df by dx a plus df by dy b plus df by dz c, which is the same as the right hand side of equation c. So we can write df by dx equal to del f into s cap. In other words, the directional derivatives of a scalar field at point in a given direction is the scalar product of the gradient of the scalar field at that point and the unit vector along with the given direction. Note that if the direction is specified by an arbitrary vector a, which is not the unit vector in that direction, the expression for the directional derivative becomes df by ds equal to del f into a by mod of a. To reconcile equations, and note that a by mod of a is the unit vector along a. Let us now work out an example on calculating the directional derivative of a scalar function using equation or example 1.3 directional derivative. Determine the directional derivative of the scalar field y equal to x y squared z cube in the direction I equal minus 2j cap plus 2k cap at the point 3, 1 and minus 1. Solution: to determine the directional derivative, we must use either equation or equation. Note that the direction is not given in terms of a unit vector. Check for yourself that the vector I cap minus 2j cap plus 2k cap is not a unit vector. Hence, we will use equation. In the first step, we determine the gradient of phi. We can find the del phi using equation A as follows: del phi equal to d of xy squared z cube by dx I cap dxy squared z cube by dy j cap plus dxy squared z cube by dz of k cap equal to y squared z cube I cap plus 2x y z cube j cap plus 3x y squared z squared k cap. Then from equation, the directional derivative in the given direction is d phi by ds equal to y squared z squared I cap plus 2x y z cube j cap plus 3x y squared z squared k cap of I minus 2 j cap plus 2 k cap by 3 equal to 1/3 y squared j cube minus 4 by 3 xyz cube plus 2x squared z squared. At the point 3, 1 minus 1, x is equal to 3, y is equal to 1, z is equal to minus 1, and hence d phi by ds is equal to 29 by 3. Read the margin remarks. Substituting x is equal to 3, y is equal to 1, and z is equal to minus 1 in equation 1, we can write d phi by ds is equal to 1/3 1 square into minus 1 cube minus 4 by 3 into 1 into minus 1 cube plus 2 into 3 into 1 square into minus 1 whole square equal to minus 1/3 plus 4 plus 6 equal to 29 by 3. You may now like to work out the following SAQ. SAQ 3 directional derivative. Comment this. Let us now summarize what we have learned in this unit. Summary: concept, description, scalar field, a function f which associates a unique scalar with each point in a given region is called a scalar field function or a scalar field. The curve f of xy equal to constant or the surface f of xyz constant are called the contour curves and contour surfaces respectively. Gradients of a scalar field. The gradient of a scalar field is defined as del f equal to I cap df by dx plus z cap df by dy plus k cap df by dz. It is a vector such that the change df is f for an arbitrarily small change. Dr is given by df equal to df by dx dx x plus df by dy plus df by dz dz. Del f into dr. Properties of gradient. The gradient of a scalar field is a normal to the curves of constant value or surface of constant value of the scalar field. The gradient of a scalar field at a point gives the direction of maximum rate of change of a scalar field. Directional derivative of a scalar field. The directional derivative of a scalar field f in the direction specified by the unit vector s cap is equal to s by s is df by ds is equal to s cap del f is equal to s by s del into del f. It is the projection of delep on S cap. Terminal questions. Comment this. Solution and answers.